Good evening, everyone. Myself, Dr. V. Jayalakshmi, Professor, Department of EEE, Bharat Institute of Higher Education and Research. As a coordinator of this FDP, I welcome you all for the AICTE Training and Learning ATAL Academy sponsored 6 days online faculty development program on recent trends and advancement in integrated power systems. It's my pleasure to introduce our today's resource person, Dr. B. Rajanarayana Prushti, Senior Member of IEEE, is a Professor and Director, Research and Innovation, Sankal Chand Patel University, Gujarat. He obtained his PhD from National Institute of Technology, Karnataka. He has 16 years of teaching and research experience in esteemed institutions like Vellore Institute of Technology, Galkotias University, Alliance University, and NIST universities. His research area includes data processing, time series forecasting, high dimensional dependence modeling, and applying machine learning and probabilistic methods to power system problems. He has published more than 60 papers in SCI journal, and he has presented 50 papers, more than 50 papers in international conference. He has authored more than 10 book chapters, and he has co-authored a textbook entitled Power System Analysis and Operation and Control in AICTE International Publishing House Private Limited. He has also edited 2 books for CRC Press. He is the associate author of Journal of Electrical Engineering and Technology, International Journal of Power and Energy Systems. His exceptional research work has led him to prestigious POSOCO Power System Awards for 2019 by Power System Operation Limited in partnership with IIT Delhi. In recognition of his publication from 2017 to 2019, he was awarded the University Foundation Day Research Award from BPUT, Odisha. He received the Young Professional Research Award from NIT Meghalaya, recognizing his outstanding professional and research achievement in energy technologies. He has been active reviewer and has reviewed more than 600 manuscripts. So we are truly honored to have him share his insights and expertise with us today. Thank you all. Now I hand over the session to our resource person.
Thank you, madam, for this introduction and inviting me for this FDP as a resource person. So, is my screen visible?
No, sir. Now it's visible, sir.
Can you see my slides?
Your slide is visible only, sir.
Yes. So, thank you very much to the organizing team from this university. So, first I will congratulate to the organizing team for getting successful approval for this FDP in online mode. And today's topic of discussion is probabilistic load flow analysis, and it will go for around 90 minutes. So, madam has already highlighted my research credentials, so I will not be wasting much of my time here, and directly I will go to outline of my presentations. So please update me if in case you are not able to find slides moving, so that I will take necessary action and do the needful.
Okay, sir.
Yeah. So today basically we will be covering in this discussion the difference between conventional steady state load flow analysis and probabilistic load flow analysis. Then since this is a research topic, we will come across certain literature on this particular topic, and what are the new technologies, methods, modeling frameworks that are coming up in this particular area, we will cover in a comprehensive manner. Then we will also touch upon over limit risk assessment, and we will cover sensitivity metrics based steady state analysis, and then we will conclude the presentation. So, see, in the conventional load flow analysis, we consider the nodal powers has fixed values, and we then determine the steady state values of the state variables, bus voltage magnitudes and bus voltage angles. And if we can calculate voltage angle and voltage magnitude, it becomes easy for the other variables of the power systems to get calculated, like branch power flow, slack bus power requirement, losses, and all can be obtained if bus voltage magnitudes and bus voltage angles are calculated. But in general, this fixed value assumption of nodal power is not realistic. It is because these values, these load powers, generations are uncertain, and for the situations where renewable generations are getting integrated to the existing conventional grid, it becomes more difficult to obtain the fixed values of nodal power. Since they are uncertain, we consider them as random variables in probabilistic load flow. And any random variable can be represented as a probability distribution, and therefore the state variables and other power system variables will also be random variables, and probability density functions or probability distribution functions for those variables will be obtained. Am I audible? Hello?
Yes, sir.
Am I audible, madam?
Yes, sir. You are audible, sir. You can continue, sir.
Yeah. So, coming to this uncertainties, these uncertainties are associated with the load powers, the renewable generations like photovoltaic generations, wind power generations, and now when these buses at various buses in the power systems are located across various places, so the generations at those buses are also correlated in space and correlated in time. So the type of correlation in time, we call it as temporal correlation, and the type of correlation in space is called as spatial correlation. And when we consider the correlation in time and space, one has to consider spatio-temporal models for this particular analysis. Now, uncertainty with various inputs being unknown a prior, it is very difficult to design, plan, operate a power system when it is looked from a probabilistic viewpoint. Therefore, probabilistic load flow is vital because its outcome will help calculate the risk indices to recognize the weakness of the system and to take necessary action to make the system more robust. So in order to perform this probabilistic load flow, there are three major steps one has to follow. First is the input uncertainties and the associated spatial and temporal correlations must be modeled accurately. Then for the existing power system, suitable model must be defined, and then A probabilistic load flow method must be used to calculate the probability distribution for the state variables and the output variables. So here the state variables are the bus voltage magnitudes and angles, and the output variables are real and reactive power flows and losses in the lines and slack bus power requirement, all those things. So coming to the literature, how this uncertainty analysis and modeling has been done in the literature based on the historical time series data of power system inputs. So when I say power system inputs, I basically uh, keep in mind that I'm talking about the load powers, the conventional generations, and non and renewable generations that are connected at various buses in the power system, and we call them as nodal powers. So each bus is a node, so these powers are the nodal powers which are uncertain, they are not fixed. So conventional load flow considers these values as fixed, and probabilistic load flow considers these variables as random variables. That means it has a mean value, and also a range of variation defined by a probability distribution. So when uncertainty modeling is to be talked about, we have to define which kind of uncertainty one has to model, whether it is a planning uncertainty or it is an operational uncertainty. So planning uncertainty is basically to make a modeling of or quantification of this uncertainty is basically to help engineers make decisions regarding investments in locating adequate generation transmission assets at suitable place and time. However, the operational uncertainties is basically quantified to recognize whether the power system's operating limits are within acceptable reliability criteria or not. So accurate uncertainty modeling can be developed based on the adequate historical data for those inputs, low powers, conventional generations, and renewable generations. So either the unpredictable uncertainty component is required to be quantified for planning uncertainty model, or expected value and the corresponding confidence interval of the future value can be forecasted for operational activities in the power system. So when we talk about various activities, we basically classify them into three categories: expansion planning, operational planning, and real-time operation. So time horizon for all of these three activities can be either long term or medium term or short term. And for each of those time horizon, the time scale, time step, and action and decisions that basically is taken is highlighted in this table. Now coming to modeling of uncertainty for a planning study. So when we consider a planning study, year length data is required, and for such a study, each day one sample will suffice the purpose. So for load power, photovoltaic generation, wind power, conventional generation, a daily time step data is to be taken and will be treated as a random variable, but its mean value and uncertainty must be calculated. So historical observations collected at a daily time step. When I say time step, it basically the time interval. So daily time step indicates each day one sample with a gap of 24 hours. So if I collect a sample 12 o'clock 12 o'clock noon today, then the next sample will be 12 o'clock noon next day. So such kind of data is basically suitable for a planning based uncertainty modeling. So when we take such a data, and if we can find a variability being present in the data, so that variability can be considered as a predictable variation. And once we remove that predictable variation, we will be obtaining the unpredictable component, which is referred to as the uncertainty component of that particular variable. So the main challenge here in the uncertainty modeling of a daily time step data for planning studies is basically to model the predictable variation such that it can be removed from the data to obtain the unpredictable variation, which is the uncertainty component in the time series or the input random variable for the probabilistic load flow. So this particular removal of predictable component or deterministic component from the given time series is referred to as pre-processing, time series pre-processing, and the various steps in the time series pre-processing is collecting the historical data for a particular input random variable, then to update the missing values if there are any, and then to estimate the predictable periodic variation, and then remove the periodic variation to obtain the unpredictable component, and then to fit a probability distribution to the uncertainty component to characterize its density function. So since I have already highlighted these input random variables at various buses are correlated to each other, associated to each other in space as well as time. So it is imperative to go for a spatio-temporal model which can be used to generate the samples of future, which can be then used for an operational planning study, which majorly requires the following steps: pre-processing, transformation technique, PCA, principal component analysis, and a suitable time series model for forecasting. So this is the supporting literature where this unpredictable uncertainty modeling is done by removing the predictable component, and a few studies have considered the load power time series, few studies have considered the renewable generations, few studies have considered the temperature, and then they have modeled the predictable variation, and then they have removed it from the data to get the unpredictable variation. Coming to the second aspect, which is the power system model. So our power system is a very vast system, and we can either use the actual model, which is nonlinear, you know this, because the injection variable expressions, if you see, they are containing the sine and cosine functions, and it is a nonlinear steady state equation. Or you can go for a sensitivity matrix based model, which is a linearized version of the actual nonlinear model. So depending on whether the system is a transmission system or distribution system, the modeling formulations differ.
मी लावून दिला असतं तुला व्यवस्थित करून संध्याकाळीला.
Hello.
Yes, sir. I have muted, sir. Sorry for the disturbance.
So am I audible, madam?
Yes, sir, you are audible only, sir.
Yeah. Then there are certain supporting literature for this modeling formulations. Few studies have considered the linear models, and few studies have considered nonlinear model. When it comes to linear model, again, either it is a Dishi model or with some certain approximations. And then most of the studies have considered that resistance of the conductor, transmission line conductor is fixed. So I'm basically talking about the transmission systems. Most of the load flow models consider that this resistance of the conductor is fixed. However, we know that this resistance of the conductor, which is prone to ambient activities, is basically depending on the temperature of the ambient. So the ambient temperature variation affects the resistance value. So certain load flow models have been developed considering this temperature effect, and not only they consider the electrical parameters but also the electrothermal parameters, thermal activities also. So one such work is done in this paper where they introduce the temperature augmented load flow, where temperature effect has a dominant impact on the branch power flow and losses. And coming to the third activity, which is the probabilistic load flow method, we otherwise called as uncertainty handling method. So if we know the probability distributions of the inputs, then how can we calculate the probability distributions of the output for a given relation between output and input? Is what exactly a uncertainty handling method's responsibility is. So this uncertainty handling methods can be broadly categorized into three types. They are numerical methods, approximate methods, and analytical methods. These numerical methods actually use the actual nonlinear power system models, and they then use the conventional NR method to numerically calculate each value of output random variable for a given set of input random values, random variable values. So it is considered to be more accurate method of handling uncertainty. But the demerit of this method is that it takes more time, because if the uncertainty spread for various input random variables are high, then the number of samples required, which will suffice an accurate obtaining of output variables uncertainty value is more. So in that case, those sample size can be optimally selected by using certain mechanisms, and then the method becomes an approximate method. And when coming to the analytical methods, they use a linear relationship between outputs and inputs, and the obtained results are faster. However, uh, accuracy is compromised. So in a planning based studies, accuracy to certain levels can be compromised, but in operational studies, accuracy
Sir? Sir? Dr. Rajanarayanan, sir? Dear participants, kindly wait. Resource person has faced network issues.
Is my screen visible, madam?
Yes, sir. Your screen is visible only, sir.
So, am I audible properly?
Yes, sir. You are audible.
Yeah, so based on the type of study, whether it is a operational study or expansion planning, or it is a real-time operation, the apt method can be selected. So this numerical method is basically the Monte Carlo simulation with a simple random sampling, and it relies on repetitive random sampling, and it is regarded as the most accurate method to validate the approximate and analytical methods results. So if someone is proposing an analytical method which takes less time to calculate the values, but the accuracy of those values can only be compared with the numerical method. And similarly, approximate method uh, takes little more time, little less time than the numerical method, but its accuracy is much better than the analytical method. So approximate method is a compromise between numerical method and analytical method. So for operational studies where results must be obtained faster, an analytical method is an apt method, and there are various analytical methods have been proposed in the literature. They are convolution-based analytical methods, Gaussian mixture model-based methods, and cumulant-based methods, and hybrid methods. And there are analytical methods which cannot incorporate the input correlation, and there are methods which can incorporate the input correlation, because correlation is a very important concept in probabilistic load flow, because when we consider them as random variables, and random variables correlation affect the output variables value. So accurate modeling of correlation in addition to the modeling of input uncertainty is pivotal. So what are the research opportunities? The existing methods, I basically talk about the analytical methods for characterizing input uncertainty have not been adopted and adequate pre-processing, and the pre-probabilistic load flow inputs are influenced by geographical, environmental, and social factors. So a thorough understanding of physical phenomena to ascertain actual influencing factors is very important. Multi-time instant pre-processing is also necessary to ensure actual and predictable component of uncertainty at various time instants. So not only it is important to know the uncertainty variation at a particular time instant, but at various time instant is also important. The effect of ambient temperature uncertainty on branch parameters like resistance and reactance of the conductors is not explored in the PLF studies, and it would be better to have information of risk values at multiple time instants such that the operators and planners or the engineers, power engineers can take effective decisions with regard to system reliability. Impact of various PV penetration or wind power penetration and their associated correlations on risk assessment is also not explored in a greater way. And further improvisation of sensitivity metrics for an analytical method based PLF calculation is also important. So the existing analytical methods, when considered on a scale considering uh, simulation time and accuracy, we can see the method of interest would be definitely at a place where accuracy is of accuracy in less simulation time is of more priority, and always the methods which are existing presently for analytical under analytical umbrella, that is dependent discrete convolution, Gaussian mixture approximation, sequence operation theory, and these all must be hybridized with certain other methods which can reduce the simulation time and can obtain high accuracy in the obtained probability distributions. Yeah, so am I audible? Am I audible?
Yes, sir, you are audible only, sir. You can continue, sir. Okay, sir.
Yeah. So present research focus of researchers is a detailed uncertainty analysis and probabilistic modeling for probabilistic steady state analysis. Probabilistic load flow is a steady state analysis. So probabilistic load flow we generally refer to as probabilistic steady state analysis. Over limit risk assessment under various penetrations and input correlations, considering electrothermal coupling effect of branches, transmission branches, is also one of the important research going on recently. Then sensitivity matrix based load flow, probabilistic load flow calculation for operational study is also very important, where forecasting role is coming into picture based on the input pattern, the forecasted value of the output in terms of probability distribution. So then the forecasting becomes a probabilistic forecasting. So conventional forecasting is nothing but our deterministic forecasting, which forecasts only a single value of the inputs. And probabilistic forecasting is forecasting a PDF or a confidence interval, which can then be used for the probabilistic load flow in operational studies. So coming to effective pre-processing, it is challenged to construct a model which will characterize the predictable component in the data, because I had already highlighted that modeling the predictable component in the data is important, because it is that data, it is that model which when subtracted from the actual data will yield the unpredictable component. So a suitable model selection, a suitable regression based model selection is very important. So in modeling that predictable variation using a regression framework, the main challenges that come across are the complex trend characteristics in the data, and obtaining clues for the existence of seasonality order, which basically indicates the periodicity in the data, and then identifying the type of seasonality and ensuring a best fit model are various main challenges. So let us discuss how this predictable variation can be modeled for a planning based study using a regression framework. And the input we have considered is photovoltaic generation. So since we know a planning based study basically considers year long data, and more the data set at hand, more the size of the data set at hand, the more accuracy is the obtained result in the uncertainty model. So on this note, three location PV generation data we have collected from America, from Moncton, Parksburg, and Lincoln, and they are specially correlated to each other, and they are located at distances of 73, 120, 130, 128, 130 kilometers from each other. And when we looked at the data, we could see a skewness, multimodality in the data. And further, we observed annual periodicity in the data and with some decreasing trend. And these annual predictable variations are found to be deterministic because they are getting repeated year by year. So let me show those patterns. So these are the patterns we could observe. So we have considered 5 years data, but we have quoted here for only 2 years. And you could see whatever is the pattern, it is getting repeated each year, right? So daily one sample we have collected. So in 2 years, we have 365 into 2 samples, which amounts to 730. So we have plotted 730 samples, and you can see yearly the data is periodic. And you can see two modes appearing in certain pictures. And also there are some skewness, left skewness, right skewness in the data set. And also it can be observed in the last figure that multimodality and skewness both are present in the data. So what actually causing these effects in the data? So we then identified the solar elevation angle, solar azimuth angle, and solar incident angle, which creates those multimodality and skewness in the data sets. And then we considered a regression model, multiple linear regression model, and we considered these three sine theta s, sine gamma s, and cosine of theta as the regressors. Two more extra regressors for trend effect are also considered, and then the error value, which is the unpredictable component, is estimated. The model parameters A, B, C, D, E are calculated using ordinary least square method, and you can see by accounting the trend effect model and multimodality, we could find a decrease in the coefficient of variation in the uncertainty component. Lesser the coefficient of variation, best fit is the model is, and considering all the 5 terms, 5 regressors, we could obtain the least value of coefficient of variation, which is 50%, nearly 50%. Am I audible?
Yes, sir, you are audible. You can continue, sir.
Now, as I had highlighted initially, there are 5 major steps for the pre-processing. So first is the collection of data and missing value updation. Then the second step is the daylight time saving adjustment. Then modeling the predictable variation in the data, and then removing the predictable variation from the actual data to get the uncertainty component, then to fit a probability function to the obtained unpredictable component. You can see in the last block, the y-axis is probability density and the x-axis is the photovoltaic generation, and the area under the density plot is 1. And this is the probability distribution of the PV1, which might be present at a particular bus in the power system. So instead of taking a fixed value for the PV, we have now considered a probability density. Now this is done for all the 3 PV arrays we had considered, and we could see after pre-processing there is a dramatic change in reduction in the coefficient of variation and standard deviation of the data. Now coming to load power and ambient temperature. At different time instant, the daily time series of load power and ambient temperature exhibit nearly the same pattern of variation. At different locations, the patterns are extremely varying. So there are evident periodic variations like PV generation, but there are no definite trend behavior like PV generations. So this complex trend behavior is the main reason or the main setback to come up with a standard modeling framework. Further, the seasonality factors present in the data is very difficult to extract. So the existing approach, like the way we followed for the PV generation, cannot be straight away used here, because identifying the apt regressors for the load power and ambient temperature is not that straightforward as that was for PV generation, and therefore a regression based method which is a befitting for this particular extraction, choosing the regressors in this particular model is really difficult. And a new regression model can be considered for this particular case of load data and ambient temperature. So what we can do is we have to find out the dominant frequency components. So seasonality or the periodic variation, whatever we are talking about in this particular research, is basically the concealed frequency components. Because it is the frequency component which gives the variation. So if we can know in advance what are the frequency components present in the data, then we can use those frequency components as a sine cos regression model in the MLR, and then we can model the predictable variation. Now, there are certain criteria for the model selection. So how many frequency component to be considered in the model using Bayesian information criteria, and this is the BIC score, and less the BIC score, more accurate is the model. And we have considered our proposed model M4, using this approach, and we are comparing our results with the existing models M1, M2, and M3. So this is how the data sets of load power and photovoltaic generations looks like. And you can see um, the pattern is very complicated, and the same set of steps we had adopted uh, in the load power and photovoltaic generations, and we then could see the output is the probability density function of the load power and ambient temperature, and we calculated the score, BIC score, and the lowest score is obtained in case of the M4 as indicated against M4 in the figures. In all the cases, the M4 is yielding the lowest BIC, and for various figures shown in the previous slides, the frequency components, which are basically the regressors, are highlighted. So trend terms are also indicated, and harmonic orders are also, frequency components are also indicated. And then the coefficient of variation, standard deviations, and mean values are also indicated here for temperatures at Lincoln, Mangalore, Coimbatore, and Berhampur. Then planning-based studies basically require the unpredictable component. But as I had already mentioned, for an operational planning study, we have to go for a spatio-temporal forecasting model. So for a spatio-temporal forecasting model, not only the spatial correlation, but also the temporal correlation must be taken into account. So in order to prepare a model that extracts the spatio-temporal correlation and uncertainty in the data, first we have to check the available association between various variables. You can see there is a high level of linear correlation, linear dependence between the variables, and you can see when I remove predictable component and plot their scatter plot, you can see across the uncertainty, the scatter plot of the residual seems in a very circular manner, and principal components for each can be shown here, which are actually the uncorrelated components. Then we will find out the forecasted values using any model, a regression based auto-regression model or conditional heteroscedastic models. Then we incorporate the correlation effect among the forecasted values. The next important task is the deterministic model, system model, as I have been telling you, whether it is a DC model or a actual AC model or a sensitivity based linearized model. In all the models, we consider the resistance of the conductor is fixed, but in reality, a resistance depends on a temperature, and there is a electrothermal correlation, right? There is electrothermal correlation. You can see here, there is a electrothermal coupling effect. So you can see the resistance depends on the loss. Loss depend on the temperature. Temperature again depends on the resistance, again depend on the temperature. So between this loss temperature and branch temperature and branch resistance, there is a electrothermal coupling, and the associated formulas are shown here. So let us update our model, sensitivity matrix based model. So temperature is nothing but the ambient temperature of any conductor. So here Tij basically indicates temperature of the branch connecting ith bus and jth bus. Is nothing but ambient temperature plus the rise in temperature. And this rise in temperature can be represented as R theta P loss. So this R theta, we call it as thermal resistance, which can be calculated as the ratio of rated rise in temperature and rated power loss. And this rated power loss can be calculated using equation 4. And therefore, in the error matrix and the mismatch vector, we can include delta t days using this particular expression. In the first line, whatever expression Tij days equal to Tij minus R theta P loss, which is equal to the ambient temperature. So the sensitivity matrix is now revised in equation number 5. So this del, delta, del, V, del, T are the state vectors. So in the conventional load flow, our state vectors are voltage, magnitude, and angle. But in probabilistic load flow, our state vectors would be voltage, magnitude, angle, and temperature. Whereas in the mismatch vectors, we had only delta P, delta Q, which are real power mismatch, reactive power mismatch. But now we will have delta T days, and delta T days is nothing but delta T ambient. So T ambient is now included in the mismatch vector, and temperature of the conductor is now included in the error vector. Using that, we can calculate the risk indices like under voltage probability, over voltage probability. Now, when we see figure 16 here, it is very evident that even though the probability of exceedance of a random variable value for two different cases may be same, but the main values from the threshold value is at a different distance, which indicates that not only probability is important in calculating the risk, but also deviation from the threshold value must also be considered, taken into account. Therefore, probability and severity both must be multiplied to get the final value of the risk indices, which is discussed here. So we can calculate under voltage probability, over voltage probability, over load probability, and so these are all various other risk indices to be calculated. And this severity functions now can be considered, so we can penalize more it is deviating, more the mean value is deviating, more penalty should be given. So this penalty can be exponential functions or linear functions. We had considered in this particular study the exponential functions, and we calculated the risk indices using the over probability, over limit probabilities, and severities. And various risk indices that are generally of interest is risk of system overvoltage, risk of system overload, risk of system thermal overload. Now let us consider a case study here. We have considered a 39 bus system, and at three buses, bus number 29, bus number 26, 27, and 28, we have connected three photovoltaic generations. Although this generation are collected from three different places in America, we just have considered here to see how it is going to affect the probability distributions of the state variables and output variables. So we have considered the loads connected at the buses 9, 18, 21, 23, 24, 25, 26, 27, 28, 29 as random variables, and the remaining load as constant values, and ambient temperature of the temperature dependent branches are assumed same, and the real load power at buses 21, 23, 24, 25, 26 are assumed to follow Gaussian distributions. Now you can see we are also interested to check when the PV penetration level is increased, how it is going to affect the risk values. So you can see when the PV penetration increases, the patterns remains the same, which is multimodal, but the spread is increasing. It is scaled up for various penetrations. The variation is high. So when we compare the probabilistic load flow and temperature augmented probabilistic load flow results, you can see uh, various power system variables like real power flow, voltage magnitude, real power loss, and reactive power loss. You can see there is a drastic change in PLF and TPLF results, indicating that effect of ambient temperature in the probabilistic load flow result is imperative. Also, we could see how the error is in the calculation of various output variables, power flows, when temperature effect is considered in the resistance calculation, and if temperature effect is not considered in the resistance calculation. And various risk indices are also calculated for 20% of penetration. And you can see in this table that with the increase in the penetration, the under voltage probability increases, the over voltage probability decreases, the overload probability increases, the temperature overload probability is also increases. Further, it is very important to note here that when no correlation effect is considered and when correlation is considered, the results are dramatically different. So not only different penetration cases must be analyzed while designing and planning a power system, but also the associated correlations must be considered to ensure that the system is reliable. And here cumulative probability distribution of various uh, net load at buses 26, 27, 28 are shown, and the risk index, risk of system over voltage, risk of system overload, and risk of system temperature overload for various penetration level, considering and without considering base case correlation is indicated. Now, as I had been telling you, the traditional PLF model is not considering the temperature effect, and we can have a temperature effect model, and this sensitivity based matrices can be used for the application of a analytical method. Numerical method directly uses the nonlinear equations, but a sensitivity matrix based model is used for analytical methods. And also I have highlighted in my previous discussion that a hybridization of analytical methods can better include the correlation effect, and therefore three dominant analytical methods such as extended cumulant method, Gaussian mixture approximation method, and sequence operation theory are individually considered. Their merits, demerits are highlighted, and then how the merit, how the demerit of a particular method can be compensated by others is identified, and then proper hybridization is made combining cumulant and Gaussian mixture approximation, then cumulant and sequence operation theory. Now, this sequence operation theory is basically convolution based, and cumulant, extended cumulant can effectively include the correlation. Sequence operation theory cannot incorporate the correlation. So a hybridization can calculate accurately the results by considering the correlation. Four cases considered.
You can continue, sir.
Am I audible?
Yes, sir, you are audible, sir. You can
Yeah,
continue.
So three basic operations in the sequence operation theory is the ATC, STC, additive type convolution, subtraction type convolution, and we have first tested by considering four cases the accuracy of these operations, and when compared to MCS, you can see very accurately they calculated the estimated the values. And then this is the mechanism by which across Gaussian and non-Gaussian components correlation is calculated, and then a Gaussian copula density function is used to find out the or to accurately model the correlation effect. And finally, when we compare the traditional and modified PLF method, you can see the error found to be non-zero for traditional method and MPM, modified method. This effect of correlation is studied for 5 different cases systems. A New England 39 bus system where TPLF is employed, IEEE 118 bus system where PLF is used, New England 30 bus TPLF for correlation type 2, then 14 bus for correlation type 3, then 118 for correlation type 3. And we could see there is for different PMCC product moment correlation coefficient of 0.5 and 1, the mu and delta effects are observed. Although the correlation is not having any effect on the mu, but correlation has a effect on the sigma, which is the standard deviation. Similarly, the hybrid method's accuracy is also compared with respect to the existing methods uh, and, for different model parameters like G, which is the number of components in the Gaussian mixture model, and delta S, which is the step size which is to be used in sequence operations. And accuracy of those with respect to various values of G and delta S is plotted in the figure for a particular case of real power flow. And the hybrid methods simulation time is also compared, and the proposed methods here are univariate CCGMA, multivariate CCGMA. So CCGMA is basically the hybridization of cumulant and GMA, and CCSOT is the hybridization of cumulant method and sequence operation theory. And these three methods are proposed methods, and the result is compared with CCGCM, CCCFM, discrete convolution, and MCS. And you can see the time taken by the CCGMA and CCSOT is less compared to the other methods. The accuracy can also be seen here. Red plot is the MCS plot, and all proposed methods are approximating nearly to the probability, cumulative probability plot of the same variable using MCS. Since MCS is most accurate method, it is always considered as the reference method for calculating the accuracy or to check the accuracy of the obtained probability distributions of random output and state variable random variables using a PLF method. Now coming to a spatio-temporal based temperature augmented probabilistic load flow study, a 39 was system in New England system is used, and you can see 5 photovoltaic generations are installed, and These are the steps to obtain the PV generation time series. We collected the radiation data, and using the solar radiation data, we have calculated the PV generation output using the formulations as shown in the table. And then we have calculated the probability density plots, cumulative probability plots for real power flow in 37-38 branch and 41-42 branch. So this particular study summarizes various probability load flow methods and their applications to power systems, whether it is a planning based study or operational based study or real time operation. So that's all from my side, and this is the forum is now open for discussion.
Okay, sir. Thank you, sir. Dear participants, if you have any queries, you can ask. Participants, you can post your queries in chat box also. Dear participants, any queries? Sir, if no queries means, shall we wind up, sir?
Yes, yes.
Okay, thank you, sir. Thank you so much, sir. So, on behalf of Bharat Institute of Higher Education and Research and ATAL Academy, I sincerely thank Professor Dr. B. Rajanarayanan Purishri, Professor Director Research and Innovation at Sankal Chand Patel University, for delivering an enlightening and impactful talk on probabilistic load flow analysis. So the session was engaging, thought-provoking, that will enhance both our academic and learning professional growth. So we truly appreciate your time, effort, dedication in sharing your expertise with us, sir. Thank you so much, sir.
Thank you, madam, for this opportunity for inviting me for this particular online FDP. And this is a very regarding uncertainty modeling and forecasting and probabilistic load flow. So I encourage all the audience, all the participants to write research papers on this particular area. And my email and contact numbers are available with you. So at
Yes.
any time, if you feel like having any discussions, you can
Okay.
contact to me. That's all from my side. Thank you very much. Good luck to the participants and good luck to the organizing team.
Thank you very much. Thank you, sir.
So can I leave the meeting now?
Yes, sir, you can leave the meeting now, sir.
Okay.
Dear participants, you can leave this meeting and join the session, next session. Next session will start from 3:30.